Madam Chancellor, Carleton graduates, and guests, it is my pleasure and privilege to introduce our honorary doctorate recipient, Dr. David Sinclair. Dr. Sinclair completed a PhD in nuclear physics at Queen's University. He pursued postdoctoral work at the Niels Bohr Institute in Copenhagen before becoming a university lecturer in the Department of Nuclear Physics at Oxford University and an official fellow of St. Anne's College. He returned to Canada to play a lead role as Deputy Director and Associate Director Science in the development of the Sudbury Neutrino Observatory, SNO, while working at Carleton University. Dr. Sinclair's research has focused on studies of neutrinos, the most abundant particle with mass in the universe, but the least understood. Work at the Sudbury Neutrino Observatory showed, for the first time, that neutrinos have a non-zero mass and that they have unusual properties that may help to explain some of the cosmological mysteries surrounding the Big Bang. These results led to the awarding of the 2015 Nobel Prize in Physics. Following the completion of the SNO experiment, Dr. Sinclair directed the construction of a large laboratory, the SNO Lab, to study neutrinos and search for elusive dark matter. His work was recognized in 2006 with the inaugural Gold Medal for Research Achievement at Carleton, the Natural Sciences and Engineering Research Council Polanyi Award for Research in 2007, the CAP Triumph Bott Medal for contributions to subatomic physics in 2011, an honorary Doctorate of Science from Queen's University in 2012, and the Breakthrough Prize in Fundamental Physics in 2015. Dr. Sinclair was named a Davidson Dutton Research Lecturer in 2003, an elected Fellow of the Royal Society of Canada in 2004, a Chancellor's Professor at Carleton University in 2009, and an Officer of the Order of Canada in 2018. Madam Chancellor, in recognition of his truly outstanding contributions to the field of experimental subatomic physics and for his leading role as the founding director of SNO Lab, I request that you confer the degree of Doctor of Science, honoris causa, upon Dr. David Sinclair.
By virtue of the authority vested in me by the Board of Governors and upon the recommendation of the University Senate, I confer upon you the degree of Doctor of Science, honoris causa. It's a pleasure and an honor.
Thank you so much. Madam Chancellor, Mr. President, graduates, and honored guests. It's an honor indeed to receive the degree of Doctor of Science from Carleton University. It's also an honor to have the opportunity to speak to the graduating class in the faculties of Science and Engineering. My heartfelt thanks to everybody who has made this possible. All the graduates here today have passed one of life's major milestones with completing their degrees. And I think it's appropriate to pause for just a few moments and think about the significance of the milestones. To reach this point, you have learned a lot. You have learned lots of numbers, constants, equations, etc. I suspect that many of these have already found their way to the dustbin as you left your final exam. So what have you accomplished? Well, when I was at Oxford, the principal of my college used to speak to the incoming undergraduates, and she would tell them that the most important thing they would learn at university was how to manage their time. Now, I think all of you have learned many of these life skills, which are very important, but to me, that's not the prime purpose of a university. I think what you've learned is how to learn, and I'd like to just focus on that for a few moments. And so I'd like to tell you a few examples from my career of how this ongoing learning has been so important and will be so important to you as you go forward with your careers. As it was mentioned, most of my important research was done at the Sudbury Neutrino Observatory, and as it was mentioned also, what we were able to demonstrate that the most abundant particle in the universe, by far, billions of times more neutrinos in the universe than there are electrons and protons and the things which you've been studying, and we know so little about them. We were able to demonstrate for the first time that these particles actually have mass, which has great significance to particle physics, but they also have peculiar properties which we could show that influence what happens in the Big Bang and could explain some of the mysteries that we really don't understand in the Big Bang, the start of our universe. To make these discoveries, we had to overcome many obstacles. I think I had to learn something about every discipline that's represented in the graduation today. And I'm going to just mention a few of these. Our detector for seeing neutrinos consisted of 1,000 tons of heavy water surrounded by 7,000 tons of regular water, both of which had to be extremely pure. I did a feasibility study for this project at the very beginning of our studies and realized we'd have to excavate the world's largest cavern 2 kilometers underground that had ever been contemplated that was safe for people to go into. And this, of course, is a very specialized form of engineering that we had to adopt. We had to use almost every form of engineering in order to achieve this experiment. The area where I focused most of my effort was how to make the water clean, because the detector's almost all water, and any radioactivity in that water would give a little signal that looked just like a neutrino. And let me explain that the signal we were looking for was a tiny flash of light coming from this monstrous detector, almost as big as this room. It's a little flash of light. It's about as bright as if you take a candle and you look at that candle, but now you put it on the moon. That was our signal. And so any of this radioactivity would swamp the signals we were looking for. So I thought, this is a chemistry problem. I'll consult my chemistry colleague at my college, St. Anne's, and I told her we need to measure thorium in water at a level of a part in 10 to the 15. How do we do it? She fell about laughing. She said, the world's state of the art is a part per million. You're 9 orders of magnitude beyond what anybody's done. So we had to start to invent. My first venture actually involved biology, because I learned that there were people at that time who were studying little organisms called damids. And some of these had a property that they were very good at scavenging radium and thorium out of the water. And I thought, well, we just put these bugs in our water and then filter them all out, and they'll bring all the radium and thorium out with them. Well, that started to look a little bit messy, and so we took a different tack. And this was based on work done in oceanography. Oceanographers had found that at the bottom of the sea, in the seafloor, there are manganese nodules. And these turned out to be rather radioactive. And they're radioactive because they're extremely efficient at scouring the water from the sea for things like radium. And so the oceanographers had developed a technique for looking at small amounts of radium in water. And I should mention the level of radium we wanted to measure was 1 atom per ton. I didn't mention that to my chemistry colleague because I thought my reputation had taken enough of a beating for one day when I talked to her. But that was our target. So the oceanographers had developed techniques for doing this radium tracing, and they used it for tracing, for example, how water flows out into the ocean from river estuaries and things, because they could trace the radium from coming out of the ground and see where it went. So we took that technique, and here at Carleton, we've assembled a group of physicists and chemists, and we worked to make it very, very pure. And in the end, we got the purity that was needed down at the 1 atom per ton level, and we were able then to do the physics and accomplish the objectives that we had mentioned. So I hope you have retained your understanding of learning. And what's more, I hope you've learned to love learning. This is something that will put you in good position through life. This world has many problems, large and small, and we know some of them. We always hear about climate change, and that's a huge problem that we need people of your generation to come up and solve. But it's not the only one. I think your generation will probably be the first one in the history of the world where the population is expected to peak and turn around and start getting smaller. And this is just a momentous change that we have to face. We have a very rapidly aging population. And how are we going to accomplish these things? We need your brilliant ideas and concepts and hard work to look at all of these problems. So these challenges come with many opportunities for rewarding careers. I think you have all the tools you need to go out and solve these problems. Not always the biggest one. There's lots and lots of little problems along the way. And I wish you every success in doing so. Thank you.